Okay, this is the test. Here I have the transceiver in the background, and we will lower the power. We will start off at about 7 watts. I'll key the transmitter, and as soon as I keyed it, you saw that inner flash. Now that's the inner plasma activating. Now if I take my field strength meter and I tune the apparatus a little more evenly, I'll be able to land on the working frequency that it wants to work on, which is, let's see, we almost got it, around right there, 2.416 megacycles. But because the plasma is going to heat up, it's going to burden the frequency and load it. So if I increase the power now to 34 watts, the inner part's starting to glow brighter now. I need to adjust the frequency down again. And now we're at 2.41 megacycles. I will continue to increase the power. And now we get the larger, highly evacuated globe to light up. Now I have to decrease the frequency once again to about 2.408 megacycles, and then roughly tune the antenna tuners so that to maintain low SWR. We're changing the antenna coupling right now, and right now we're at an SWR of 1 to 1, or really 1.1. Now we're at 53 watts, and I will increase power, and as you can see, as I increase the power, I'll lower it again. There's that inner sphere which seems to be expanding and contracting. Okay, now we're at 54 watts, and you can see because of its orientation and with respect to the coil, we can see that there's that bubble occurring at the bottom, and it seems to be of triangular shape. It seems to be fairly defined, but because this is an ultra high vacuum, specifically 10 to the minus 8 torr, right now it's going to start off as sky blue, but of course as we work the transmitter and RF power into the bulb for long enough, also by switching it on and off, as Tesla states, we're going to hasten the transit and also speed up the process of the brush formation. So eventually it's going to get to a white color along with a yellow tint to certain parts of the photospheres or the plasma shapes which are going to occur. So right now we're at 54 watts and our SWR is still at 1.1. Now I will increase the power. We are at 74 watts and I need to lower the frequency once again. So now we're operating at 2.402 megacycles. I will change the antenna inductance. Now I'm increasing the power again. We're at 91 watts, lower the frequency. Let's see, it seemed to shut off. Okay, now I have to lower the frequency again. Okay, there seems to be an interesting cutoff point occurring right now. So right now, the operating frequency 2.402, it's shut off at 91 watts, but now I have to increase the frequency back up again for the outer bulb to illuminate. And now we're at 2.407 watts. Now, it'll allow me to decrease the frequency slowly. While the inner part's starting to light up, let's actually reduce power. Okay. That's 40 watts. Seemed as though that the inner part of the lamp was starting to overheat. Now that's of course because the glass and the water molecules and that bulb, which there is an excess of because of it's evacuated to a lower pressure, there is of course a tendency for it to heat up more readily. So now we'll still stay at 41 watts. And I will readjust the frequency. Okay, 2.408. I'll adjust the antenna inductance. and likewise the transmitter and antenna capacitors. Okay, we have a low SWR again. Let's see, let's adjust it once more. Okay, right there. Now I will slowly increase the power. 54 watts, 57, 60 watts. So it seems to light up at 60 watts. We'll adjust the frequency down. Okay, 2.407, that's actually a little bit up. Okay, I'm adjusting the inductor. Likewise the capacitors. Okay, our SWR is a tiny bit high, so let me adjust it. Okay, the bulb went out because I had to change the SWR slightly. So let's increase it from 60 watts, 64 watts, and now we're at 69 watts. Okay, so it seems to be responding differently. This is most likely due to the effect that the bulb is becoming more sensitive. That means the vacuum inside is becoming more activated with respect to time. Now I will lower the frequency until the bulb starts to present a lower SWR. And right now we're at 2.406, so not too far from before. I will adjust the inductor once again and the capacitors. Now an interesting effect is occurring that if I retune it just by changing the output capacitors on the antenna tuner, the bulb goes out. This is an interesting effect which seems to be fairly new. Well, okay, there we go, the bulb went back in. Okay, see, we can see that part starting to heat up or emit light on the stem. Now, if I'm careful enough, it doesn't. I've had this occur before with different bulbs, and it doesn't seem as though that the glass will heat up significantly. But you just want to make sure that it doesn't overload it. Okay, that's fairly bright. I'm going to lower the frequency. I mean the power. I don't want to burden it too much. And I just went from 75 watts to now 59 watts. But we can still see that in the inner bulb there is that orange layer which is occurring if the camera could pick it up. And it's giving off a decent amount of just sky blue, very light sky blue color. Now if I just increase the power again, we're at 54 watts, and I will retune it. Okay, I increased the frequency to 2.407, and now I will increase the power respectively. Okay, the inner bulb's lit up. I lower the frequency down to about 2.402, and I will increase the power once again. 89, 95 watts. I will lower the frequency again. Oops, the inner bulb, outer bulb went out. Okay. Now, if I'm trying to adjust the SWR so it's of decent magnitude. And it seems as though that inner part really wants to heat up. I'm going to lower power. Just for reference, right now we're operating at 5 watts. And that's the amount of light that the inner bulb gives off. So of course the inner bulb is lighting up first because it is of a lower vacuum pressure. And it's a little more sensitive to RF energy, but that doesn't necessarily mean that it's sensitive in a good way. So I will end this segment and show it when it's in a more sensitive state.